And we are now live. So last time we talked about the various ways of handling these. How do we deal with these KKT conditions? So one thing worth of mentioning is that if we are in the situation as we are in chapter 5.1, that we only have equality constraints, then what we can do is we can take the equality constraints part, and we can kind of bake them into this equation in a way that we are looking for a point where h of x is 0, obviously, which h of x is the vector of all the equality constraints, and then the KKT condition itself becomes that the gradient of f plus the derivative of h times lambda is 0. The derivative here is basically the it consists of the gradients of h, different h functions, because h functions is from Rn to R, so its derivative can be thought of as a gradient. And because there are some number, let's say p, of those equality constraints, so this becomes an n times p matrix times lambda, which has lambda then has p. It's a vector of p lambda coefficients. Those are called the Lagrange multipliers. And then we can then introduce this, what is called the Lagrangian. It's the f of x plus lambda times h of x, after which we can then formulate this so that if we find the zero of the gradient of this Lz, this Lagrange function, then we find a critical point of L, but we simultaneously kind of solve those equations that are satisfied by the KKT point. So we can think of this equality constraint as just being inconsequential in some sense. Obviously, it's not inconsequential because this may be significantly harder to solve this Lagrangian method, but then solving it with, sorry, I was a little bit tired. Solving this with Lagrange, solving the zero of the gradient of the Lagrangian may be harder, obviously, than some other method, but still, it's not too bad. It still kind of reduces it into searching for a zero of the gradient. Let's moving along from that. We talked about the inequality constraints, and we mentioned this barrier or penalty method. In the penalty method, the idea is that if you the problem with the inequality constraint is that once you are inside, if you think of the inequality constraint as kind of delineating in some region of the space, so anything inside the boundary will be admissible, and also on the edge of the boundary it's fine. But if you are outside the boundary, then you're not in a feasible point. So the problem from analytical point of view, the problem with this kind of constraint is the fact that there's like a hard limit after which you can go in one direction, but you can't go in another direction. And how do you bake this into your problem is a bit hard, because we started out here. If you start just by saying, the function becomes infinite the minute you go outside the feasible region, then you lose differentiability and all continuity and all that. So the methods that work for searching for the minimum are not very helpful. But then we introduce this quadratic penalty, but it doesn't come without problems. It's because, if it's quadratic penalty, then if you are outside the region but pretty close to the border, then the penalty may be so small that it's actually, quote, worthwhile going outside the region, because the cost function decreases even as you cross the boundary, and the penalty just starts rising gradually. So what this does is it converges to a point that is actually infeasible. Let's say that you can solve the minimum, unconstrained minimum of f of x plus r times p of x, where p of x is the penalty function. Then you run the problem that you kind of converge outside the region. The idea here is that if you increase this r, which is the penalty parameter, if you increase it gradually, and iterate over and over again, then this sequence of different iterations, different solutions should converge to the optimum of this function. So the theorem states basically that under certain rather lax and reasonable conditions, assuming that the method you used to solve the unconstrained problem, if you solve the unconstrained optimization problem, if that is sound, so that it converges to an optimum of that unconstrained problem, then the sequence of successive solutions of the unconstrained problem where you increase the penalty will converge to an optimum point. So this is there are problems like discontinuity of the second derivative. We'll see some problems when we deal with this. We can do this, we can implement this in MATLAB, and we'll do this next week, or this week, sorry. So here were some examples that were dealt with analytically, and we noticed that there are points where, as R increases, these seem to converge to actual points. We talked about this example, I'm not going to go in here again. Another possibility is to increase, induce what is called a slack variable, and then make it into an equality, and then you can then transform the equality into a free problem, so that you are minimizing basically this gix plus ui squared. So you're minimizing that. That means that in order to minimize this penalty there, you're kind of looking for points that are this g of I of x can be negative, right? So it can be negative. So this has certain problems related to it, so that if you're dealing with this and the constraint function gets very negative, then it may again push it in this situation. It might push it inwards. If you find this UI is suitable UI, but the thing is, of course, obviously, it will still be a minimum, just like before, because if you think about minimizing, it's f of x plus some coefficient times sum of these squares. The sum of squares will never be negative. So even though the GI itself might offset the UI, which is the slack variable, then that's not a problem, because it's UI squared plus GIX squared should strive towards 0, and this UI squared is always positive. You see what I'm saying is that this cannot be minimized when G of I is positive, obviously, and if G of I is negative, then the UI can be chosen freely, so that this is 0. So there is no problem related to that there, and this works a little bit better in terms of second derivatives and so forth, but it is also a little bit more complicated because it introduces extra variables. Here was an example of doing that with this thing. The thing about this is that you can apply this method to also equality constraints. You can also apply this to equality constraints. Whether or not G of I is it's supposed to be an equality or inequality, it doesn't really matter. You can apply this to all of those. Here is another example that you can do. You can solve it. If it's an equality problem, you don't need to introduce the slack variable. You just take the square of the original function, because if you take x plus y minus 1 should be equal to 0, then your penalty will be r times x plus y minus 1 squared. Because x plus y minus 1, if it's different from 0, be it negative or positive, if you take the square of that, then that will always be positive. So this will always incur a penalty. And if this factor r is large enough, then this will give you, when it grows larger, this should converge to a point where x plus y minus 1 is in fact equal to 0. So this one was the other way of using this. So let's take a look at this augmented Lagrangian method. So Let's now think that we are dealing with this Lagrange method and we're dealing with equality constraints only. Now, if we take the zero of the gradient, it's not necessarily minimum of the original problem. I mean, obviously there may be many more, even if this is all, continuously differentiable and so forth, everything was fine. There may be zeros of the gradients that are, that are saddle points, zeros of the gradient that are maximum points, and so forth. So it's not necessarily a minimum of the original problem. Even if it has a minimum, global minimum, there still may be maximums and so forth. Saddle points that can exist. So let's say that we only consider feasible points. I mean, if you think about it, if you find the zero of the gradient, there is a slight chance here that is not necessarily feasible. Then in the situation where the points are feasible of this Lx lambda, then that is those are points where h of x is 0. And in that case, the value of the Lagrangian is in fact just f of x. So that's the thing to understand, is that the Lagrangian, the lambda hx vanishes at a point where x is feasible, obviously because h of x is 0. So this is obviously equivalent to the problem where you're minimizing the Lagrangian with the original constraint. But this doesn't actually seem to make a lot of sense. But if we think about this, we first transform it. This may seem senseless. We first transformed the problem into the Lagrangian, and then we reintroduce again the equality constraints. Why on earth would we do this? Well, one of the reasons why we do this is when we are searching for the points of the Lagrangian, we're actually looking at points where h of x is non-zero. And if we now then kind of reintroduce them, let's see, sometimes this kind of a trick, if you will, can help us do better. So if we introduce here a penalty method, we can augment the Lagrangian by not just taking f of x plus lambda h of x, we also take into account the square of h of x. So we take h of x transpose h of x. So basically, this is the sum of squares of these equality constraints. And we then take r over 2. This is for algebraic purposes, this r over 2. You can think of it, but just, we're applying a penalty. And now if we try to find the minimum, it still has this property that it should have the zero of the gradient. Even this, obviously, this should have the zero of the gradient should be found. The minimum of this a should be found at points where the gradient is 0. And it turns out to be like similar to the KKT condition, only now it also not only has this KKT conditions gradient equation where there's the gradient of f plus the derivative, which is the gradients of h functions times lambda, but it also has this r times h prime transpose h x is 0 because we've taken the derivative with respect to this x, although this h x times hx. So these are basically sums of squares. And it also implies h of x is 0 at that point. And now this, if we think of h of x being 0, then obviously this still has the same condition as we have from the KKT conditions. So this is just algebraic justification for why introducing this h x as square in this Lagrangian method does not break anything. It's still equivalent. So the minimum of the augmented Lagrangian is a KKT point of the original problem. So this reintroducing this or taking this as a square may introduce a situation where we are converging more rapidly towards the optimum. So we choose the initial values for this this penalty incurred for the quadraticness of this this quadratic the sum of squares of these equality constraints. We incur a penalty, and then we start with an original guess of what our lambdas are. We solve the problem by minimizing this. It gives a new point x. If we find a point where these constraints are in fact satisfied, h of x is 0, we can stop. Otherwise, we update these coefficients. Lambda is updated as a lambda plus something times the rk times h of xk. So there are other ways. This is not introduced in very great manner, but what is the point of this augmented Lagrangian method is to introduce the penalties, reintroduce the penalties, so that this is kind of like we're putting more stress on the fact that this h function needs to be 0, and then because the Lagrangian may have other 0 of the gradients where they're not minimums of the original problem, or they're not feasible or something like this, then reintroducing this kind of forces it more aggressively towards the 0 of the h function. All right. We're not going to be doing the augmented Lagrangian here. It's just a mention here for kind of like it's got this penalty method flavor that is now introduced to the equality constraint. Okay, and then the one last method that we will discuss now would be the barrier function method. So if you think of these, the augmented Lagrangian has the same penalty method flavor to it, because it kind of increases the value of the function when you are outside the feasible region. The h of x is different from 0. I know, you know, and so these have the same flavor, that when you are in the infeasible region, you're incurring something, a cost that drives kind of the free, you generate a free problem, and being outside the feasible region forces you to get closer to the feasible region, because the cost will increase the further you are from the feasible region. But there is an alternative approach to this. The alternative approach is to think that, okay, there are interior points to this problem. So where let's say the inequality constraints are satisfied, and you know, the problem comes at the boundary of the feasible and infeasible region. And as long as you are at an interior point, you don't have any problems. So one way to do this is that you force your search to search through the interior of the problem. And then if you are approaching the boundary of your feasible region, then before you reach it, you start, you know, pushing back. You generate what is called the barrier function, which means that if you try to approach the boundary from within, then there will be a cost incurred as you get closer to the boundary, so that keeps you from crossing the boundary into the infeasible region from the inside. So let's just assume that our feasible set has this, following conditions satisfied. First of all, it needs to have interior points. If it's all pure border, this won't work, right? So for instance, if we have only equality constraints, x1 squared plus x2 squared is equal to 1. It means that every point is a boundary point, because no matter what region you build out on, you know, around that point, then it will always contain points that are inside and outside. So no points in that case are interior points. So the barrier function method will not work if you don't have a non-empty set of interior points. That's why it was important for us to look into the definition of the difference between boundary points and interior points and accumulation points and so forth. So interior points are those points so that if you start with a point and you draw a circle or a ball around it, then you can make at least some small ball you can make around that point. So it consists of points that are only inside the set. So this set needs to be non-empty. There need to be interior points for this to work. Also, we need to have boundary points that are accumulation points of the interior points. What does this mean? It means is that we have to be able to construct a sequence of points that consist of interior points such that the limit is a boundary point. And for every boundary point, we need to be able to do this. So the question is, it says here verbally, the boundary points of our feasible region we need to be able to approach them from inside the region. This means that there cannot be isolated points in the space that are feasible. So for instance, let's say a situation where this might be violated is that you have this region. Let's say here's the origin of our space. I'm talking three-dimensional space, and feasible region is some let's say a ball or some blob that contains the origin. And then there's this one single point somewhere in here, somewhere a little bit further away, that is a isolated point, that is a boundary point. So if that were the minimum, then obviously we could not approach that point from the interior points. It is not said here that this is so, but the thing is, if we have a region that consists of separate regions, like let's say there is one region here and another region there, and then there are no points that adjoin these regions, then obviously there may be problems if we start from within this region and then the optimum is in the other region that is disconnected, then there may be a problem here. But I'm discounting that this is not, strictly speaking, a deal breaker, because we can still have a limit where we just jump to this other region and then start progressing from those interior points. So we define a function that maps the interior points of the region to real numbers. We define it as a barrier if it has the property that the function's value approaches infinity as x approaches the boundary. So there are some examples. If you want to think about this, then one of them is like, you think about this. G of I is negative in the interior. So 1 over G of I, the negative minus 1 over G of I of x. Let's say that we have just one G function, which in the interior of the function G of x is smaller than 0, and at the boundary G of x is 0. Then if we take minus 1 over G of x, then that approaches infinity as x approaches the point where G of x is 0, right? So this is what a barrier function might look like. A logarithm of the absolute value of G might be such. I mean, think about if you approach if G of x is negative, so non-zero and negative, take the absolute value of it, so it's non-zero and positive. If G of x approaches 0, then the logarithm of that absolute value of G of x will approach minus infinity. And then we take minus negative of that, so we will have a function that approaches infinity as x approaches a point where G of x is 0. So in this case, just like in the penalty method, we replace the original problem with a unconstrained problem, seemingly unconstrained problem. Well, it's not strictly speaking unconstrained, because we have to start at a point. We have to find points where G of x is smaller than 0. We have to go look for the interior of this region. So The penalty method has the strength that we can start anywhere in the space, and the penalty method kind of should, if the penalty factor is large enough, it should drive us towards the feasible region. But in this barrier method, we should start from an interior point of our feasible region and then, start from there. Otherwise, the barrier makes no sense because the barrier generates a kind of like an increase in the function, so that if we approach the barrier, then the function will go towards infinity before so rapidly that we will stop just short of this, even if the function f of x will get smaller, but the barrier will stop us from, reaching the actual boundary. And now, in this case, we're in the penalty method, we are outside the region, and we are outside the region, and we want to push closer and closer to the boundary from the outside in the penalty function method, because the penalty gives us a penalty, but because the cost function is also getting smaller, we kind of hop a little bit outside the region, and on that point outside the region, the penalty is just big enough to offset the small movement of the cost function that seems to get smaller. And if we as we increase the penalty, then this gap between the boundary of the region and the point we reach will diminish, and we will approach the boundary from the outside because the penalty gets bigger and bigger. In this case, we start from within the boundary, and then, the cost function seems to be getting smaller when we go there. And if we didn't have any consideration of the boundary, we would just go to the infeasible region. But this barrier method generates an increase in the cost function just as we approach this from within. So it stops us on the inside of the region, not just before the boundary. And then the barrier parameter, we tend to decrease that to make it possible to get closer and closer to the region. So whereas the penalty method in the penalty method, we increase the penalty to bring us closer and closer to the boundary, so that we get towards a feasible point from the outside. Whereas the barrier method, on the other hand, lowers the barrier. It doesn't actually lower it, but it makes the barrier kick in closer and closer to the actual boundary. So we are approaching the point on the boundary from within. So if this is the boundary, then from the barrier and the penalty method should approach the same point, only that the other one approaches from within, and the other one approaches from outside. So here's an example. The problem is that the barrier parameter, when it decreases, then we will have problems with the Hessian, and we'll see this. The condition number of the Hessian becomes problematic there. That is because the second derivative of this barrier with respect to this t parameter will become horrid and more and more horrid, so to speak. Let's say I have an example here. So we're solving the problem x1 plus x2, x1 squared plus x2 squared, subject to we have that 1 minus x1 is smaller than or equal to 0, and x plus 1 is greater than or equal to 0. So x2 plus 1 is greater than or equal to 0. So these are just straight lines, straight vertical and vertical line at x1 is equal to 1, and a horizontal line at x2 is equal to -1, and then lower left, upper left quadrant, basically, that is delineated by these functions. So we can give the constraints in this smaller than or equal to format. So g of g1 of x is smaller than, means that it's smaller than or equal to 0, where g1 of x is 1 minus x1 smaller than or equal to 0, and g2 of x is 1 minus minus 1 minus x2, and that should be smaller than or equal to 0. If we assume both of them are smaller than 0, we can start with a point which is feasible clearly, and we're not yet at the boundary. So one of them approaches. So it's going to be a region that looks like this. Using the logarithmic barrier, we can generate the barrier function, which we add the negatives of the logarithms of the absolute values of those two. And if we assume that we are in a feasible region, then 1 minus x1 becomes actually x1 minus 1, because it's the negative of that. That's going to be positive, and x2 plus 1 also going to be positive. So we do those two transformations there to get the barrier function, and now we're minimizing this function where we have f of x plus t times b of x, and then we have this cost function x1 squared plus x2 squared, and we're subtracting now because this logarithms will be very, very close to well, these logarithms will be negative, so we're subtracting t times logarithm of x1 minus 1 and t times x2 plus 1. And we set this gradient to 0. And we get these 2 points, which implies that, well, we get these points, actually 4 points. 1 plus or minus 1 is the square root of 1 plus 2t over 2, and minus 1 plus or minus the square root of 2t over 2. So the constraints to be satisfied, for the constraints to be satisfied, we need to check what happens at these. It only happens when we take the plus, not when we take the minus, because if we take the minus, then we go into a region where the constraints are not satisfied. And we notice that as t goes to 0, x1 goes to 1 and x2 goes to 0. Obviously, if we solved this and we had this t, we would decrease this t and numerically go closer and closer and closer to 0. But here we show what happens to the condition number. Remember that the condition number is the ratio of the largest and the smallest eigenvalue of the function. And if we calculate the Hessian, we get these two eigenvalues. The Hessian is a diagonal matrix, thank goodness, in this case. And so the condition number can be gotten as the ratio of these diagonals, right? And we notice that, as it's a little bit involved here, but you notice that if you just look at these two, if you take the ratio of those and you let t go towards 0 at that feasible point 1, 0, you will notice that that the condition number will be relatively poor. The condition number will approach infinity as t approaches 0. And we haven't talked a lot about the condition numbers of matrices and the condition number of the Hessian. It falls a little bit out of scope for this course. If you are interested in this, how to use this analysis in the future, then you should take the numerical analysis course. It's got a lot of discussion there. Intuitively speaking, if you have a matrix and its condition number is very large, it means that, look, you can think of, there are various ways of thinking about the matrix, what it stands for. But one way to think about it is to take a unit sphere or a unit circle or some in higher dimensions, a higher dimensional unit sphere basically, and multiply all the points on that all the vectors that point to the unit sphere with the matrix and see what happens. So what it becomes like an elongated twist. There are rotations involved and there are scalings involved. So the condition number is a
is a measure of the longest and the shortest of this dimensions of how much flattened and elongated it becomes. So in some dimensions it becomes elongated, and on some dimensions maybe flattened or less elongated even. So the ratio of the smallest scaling and the largest scaling is the condition number. And if this is a very large number, meaning that there's either a very much squeezing or very little elongating, and a lot of elongating, or in one dimension. And in this results in this can be thought of as how close the matrix is to being singular. And if the condition number is approaching infinity, then it means the matrix is approaching singularity. It's becoming singular, meaning it doesn't have an inverse. And if we think about this, what happens when we take an inverse of a matrix that is almost singular, it means that it tends to be very unstable about what it does to certain vectors when you multiply them. Because if you multiply a vector with a function with a matrix with an inverse of a matrix that is almost singular, then the inverse of the matrix when it's almost singular, then it tends to blow up certain things. Some numbers tend to go to infinity there. For instance, if we are using the Newton method and we're calculating the inverse of the Hessian, multiplying with it, we're not actually calculating, but technically speaking, mathematically speaking, it's equivalent to multiplying with the inverse of the Hessian. And if the Hessian is all but singular, then the inverse will behave in a very, very bad way. It becomes very unstable. So the problem with the barrier method is that it tends to get really icky when the t gets very small, if the optimum point is actually found at the border.
I have a question. So in which scenario this barrier method can be better than the penalty method?
In which situation? Well, there are situations obviously that can give you kind of like a situation where if you are inside the region, it's easy to find interior points of the region, and you suspect, let's say you suspect that the optimum is actually found in an interior inside the boundary. Right? So let's say that your feasible region is of a little bit of a problematic shape, but you know that the optimum is inside the region. So you don't want to use a penalty method necessarily, because you may wander off very far into this infeasible region, and maybe there are local minimums somewhere in the infeasible region. So you want to guide your algorithm, or let's say you're doing Newton method or some variant of Newton method, and you can easily find interior points, and you know that you can find the minimum by traversing in the inside of the region, but maybe the shape of the region is a little bit problematic. So the barrier method will prevent you from going too close to the walls of the region, and then it allows you to find the minimum from within. But if the optimum is actually found at the border point, then this barrier method may not be. It may result in problems like the condition number being bad.
So in this case, the barrier method doesn't work with equality constraints?
No, it doesn't work with equality constraints. You don't want to use it with equality constraints. Yeah.
Okay.
You don't want to use it with well, there's no reason to use it with equality constraints, because with equality constraints, all points are kind of boundary points, right? If you have equality constraints, then all the points are boundary points in a constraint problem. I mean, think about it. H of x is 0. Then you can only move into directions, feasible region is limited to the directions where h of x actually remains 0. So there will always be directions where you can go from that point where h of x is 0, unless h of x is trivially 0. If it increases in any direction, then going to any of those directions will take you out of the region. So any point is a boundary point. So this makes no sense. Actually, the barrier methods makes absolutely no sense if you have equality constraints.
Okay, yeah, I got it.
All right, let's have a little break now. I'm going to
the recording. So there are variants, like I said, with the barrier function. You can try this differently. This is just an example of the situation, what might happen. We can try the barrier method at the exercises. One of the problems with using the barrier method is that if you have a step length is chosen poorly, one other problem besides this one is that if you choose the step length poorly, then what may happen is that you will jump over the barrier to a point where you are on the infeasible region. And if you are in the infeasible region and the barrier function is defined like this, then it actually will literally prevent you. I mean, if you get close to the barrier, it will prevent you from going back inside. So that's another thing that may happen. We'll see examples of that in the exercises. All right. So last order of business is talk about the ellipsoid method. Remember, we talked about the bisection method. So the bisection method was working as follows. We're looking for one-dimensional, we're in a one-dimensional minimization of a function, right? With f of x, just one dimension. We know that the minimum is found probably between some point A and B. And we don't have a proper use of derivatives and so forth, but we have this general tendency of the function to first go down and then up. So there is a kind of like generalized convexity or something akin to convexity going on, so that we're going down and then up. And then we divide it again into three pieces. So we find two places in between there, and we calculate the value of the function. So we either know the value of the function at 4 points, so we know one of these, either of these three regions, either the first one or the last one. Maybe we don't know anything about the center one, but the last one or the first one will be guaranteed to not contain the minimum. We can rule that out and then move to a smaller region. So we can kind of generalize this bisection method into what is called an ellipsoid method. In the ellipsoid method, instead of us having just one-dimensional region, you can think of us as having multi-dimensional ellipsoid. Ellipsoid meaning like a squeezed version of a sphere. So we have an ellipsoid-shaped region where we know that the region contains the optimum point. The point made here is we divide the ellipsoid into two parts, and we remove one that does not contain the optimum, and we construct a new ellipsoid that contains the other half of the previous ellipsoid, so it becomes smaller. We continue until the ellipsoid is so small that this is within the margin of error. We know that this is close enough. We don't know where in the ellipsoid the minimum point is, but the ellipsoid itself is so small that knowing that it contains the optimum point is good enough for our purposes. One of the nice things about this is that ellipsoids, if you think about it, ellipsoids are convex regions. That's nice. We make the following assumptions that we have convex region, but not necessarily ellipsoid, but we have a convex region from which we are looking for the optimum. G of I being the constraint functions that we're looking for them for the minimum that is at G of I smaller than or equal to 0. And we assume that they are convex. So, the region that is produced by this inequality constraint is assumed to be convex. Strictly speaking, it doesn't actually have to be convex to be exact, but we assume convexity here. A little bit more generic version can be used in here. I'll show also the later, I mean, it's not part of this material, but we have for the later, I mean, next week or maybe already on Thursday, I'll talk about what is called the extended cutting plane method. It has a similar flavor to this. So what we're basically doing is we are making use of two things. We know where the optimum roughly is, and we have the constraints. So we're using the constraints to cut. We're cutting our region by two criteria. One, the cost function is too large in some regions, or two, the points are infeasible. And we're kind of drawing an ellipsoid around the region so that, and every step of the way, we're making the ellipsoid smaller and smaller until we are close enough to be satisfied. So if we have a positive definite symmetric matrix, here it says we're using Q inverse. So be mindful of that. But this Q inverse is also, I mean, if Q is a positive definite symmetric matrix, then Q inverse is also a positive definite symmetric matrix. So it doesn't really matter which you think of here as being positive definite and symmetric matrix. So we're looking for points X. We have X0, which is, you can think of as the center of gravity or center of this ellipsoid. So this is a quadratic form. In the easiest form, you can think of this quadratic form of X minus X0 transpose times Q inverse times X minus X0. In the easiest form, you can think of this as being just a diagonal matrix. And if you think in 2 dimensions, then if it's a diagonal matrix, then the first diagonal gives you the x-axis width, and the first one gives you an x-axis width, and the second one y-axis width. If it's multidimensional, it gives, and if it's diagonal, then it gives, each diagonal gives a dimension in this direction. So we're kind of like taking the unit sphere and then elongating it. That's the way it works. And then if it's not diagonal, then it involves some rotation, so it need not be on the axis, right? So so we can think of this as any ellipsoid that contains the optimum at this point. X0 is the center of that ellipsoid. So original ellipsoid needs to contain the at least positive volume with respect to the feasible region. So if there is an equality constraint, this algorithm doesn't work like this. So it's very hard to consider how this would work if we have a equality constraint. So think of these as having only inequality constraints. And the algorithm works as follows. So let's take G as all those functions. For simplicity of presentation, the cost function F is given as G0. So it's the 0th constraint, if you will. And first of all, we generate 3 parameters based on N. There will be A, B, and C. Don't actually worry about what A, B, and C are. So just, we can look at those later. But let's say that we choose 3 parameters. The point of these parameters is to manipulate the ellipsoids and divide the stuff into three or four regions in such a way that we can rule out one of them and generate a new ellipsoid. Right, so that's the point here. So first of all, originally, we must make sure that the ellipsoid contains the optimum. This may be tricky, but one way to do is to make it big enough to contain the whole feasible region. That's one way. Now, if there are constraint functions in such a way that that they are violated by a point xk, where xk is remember, xk is now the center of the current optimum. So if the the current ellipsoid. So if the current ellipsoid's center point violates one of the conditions, then we choose that condition. And if it doesn't violate, then we take the cost function. So like I said, we're using two kinds of criteria. One, either we rule out points because they are infeasible, or we rule out points because the cost function is very big, right? Now, I'm just gonna draw a picture to give you an idea of what might be going on here. So in 2 dimensions, I'm just gonna draw a very simple picture that might give an idea. So let's say that my region looks like, my feasible region looks like this. So I'm just, let's say that this is the shape of my feasible region. It looks like this. It's definitely not an ellipsoid. And let's say that my ellipsoid that I have drawn at this point looks like this. Okay, so my ellipsoid is this. I know for a fact that this ellipsoid contains the whole feasible region, so we're good. We're good here because we know that the ellipsoid contains the feasible region, so it must contain the optimum point. We look at the center of this ellipsoid. And in this case, in this particular case, it's infeasible. So there is one of these, the constraints that is violated here. So next order of business is we look at the gradient of this thing that is violated, if you will. So if the gradient is 0, remember these are convex functions. These are convex functions. So we know for a fact here at point 3, we're calculating the gradient of the g of s. If we chose a g that is a actual constraint function and it was convex, so this cannot have a gradient 0 because convex functions only have one gradient 0, and that is at the minimum. So if we were violating a constraint, the constraint function was greater than 0 at this point. If its gradient is 0 at that point, then there are absolutely no feasible points anywhere, so we can stop anyways, right? Because, you know, if a constraint function who's supposed to be smaller than or equal to 0 is greater than 0 and its gradient is 0, there are no points where it's smaller than or equal to 0, so we can stop anyways, right? So don't be misled by 3. So if we are here, then one of the constraints here, one of the constraints in my picture, let's say one of the constraints is violated and its gradient points there, right? And now we find the search direction. And this means we're moving the center somewhere so that in this case, we were choosing a function that was a constraint function, was violated. We move it towards somewhere. I don't know, you know, whatever it is. If this H transpose Q K HK is 0, we stop. The justification why this happens is a little bit harder to explain, but the main point of this is that if this just happens, Q is a positive definite matrix, and this means that no matter where we go here, we cannot make G again smaller. We stop because, you know, again, there isn't going to be any feasible point. So this should not happen. It's a positive definite matrix. So Q times HK will be a descent direction. increase direction. And so the negative of q times h is a descent direction. And we normalize it by dividing it with h k transpose q hk, right? So this is setting a movement. So we're kind of moving. I draw a picture here. So we draw the gradient here. So we're kind of moving the center somewhere over there, maybe. I don't know exactly where, but let's say that we move it over there. That's going to be our dk. We're moving it somewhere. And our a is now step length. We're moving this dk is going to be if we were violating, if the center of the ellipsoid was violating one of the constraints, so this dk points towards the feasible region, and a, which is now our parameter, it gives a step length. We're moving the center of the ellipsoid towards the feasible region. And our b parameter is a scaling parameter. So we're kind of making the ellipsoid's parameter such that we're tightening the ellipsoid a little bit, and it is based on how far we went and how far we were. I'm not going to mention here the proof directly, but there is the point of choosing this b here is that it makes sure that the optimum is still found within the ellipsoid. If the stopping criterion is now in place, meaning that the gradient at this point or the xk at this point is feasible and its value is gradient of f is small enough or something like this, then we stop and our ellipsoid is small enough. We know that this is very close to having found the optimum. Otherwise, we go back to step 2. There is another possibility. Now, I mentioned here that this movement of the ellipsoid in this case was about choosing a constraint function that was violated. But assuming that no constraint is violated, then the center of the ellipsoid is in fact inside the feasible region. In that case, we are going to be calculating the gradient of f at stage 3. And again, we are moving the gradient now. Moving our point in a descent direction. Remember that q is positive definite, so minus q times hk is going to be a descent direction, and we're normalizing it like this. And a, our step length, if you look at the way this a was defined, the step length is getting smaller and smaller. So we are moving by smaller and smaller steps towards the optimum. And the theorem here is that given these assumptions we made, if ever hk is 0, then we have found a minimum point. And the point is very easy to prove, because if we chose one of the constraints to be here, if we chose one of the constraint functions and we found the minimum of it, if it violates, then the feasible set is empty and there is no minimum point. So obviously that's right. So if it's a cost function, again, cost function was convex. If we find a 0 of its gradient, then again, we have found the desired minimum. The point here is that if the inside of the region does not contain any minimums of the function, any critical points of the function, then where does this gravitate towards? It gravitates towards the boundary point, which is at which the function is minimized. So whenever we are in the outside, we are pushing this is pushing the center of the ellipsoid towards the boundary point, towards the feasible region. If we are within the feasible region, we're always pushing the center of the ellipsoid towards the direction where the function itself becomes smaller. So this is only linear on that, and so on the other hand, it converges reliably so that provided that the initial ellipsoid actually was found to be good. So there are possible ways of doing this, is that you can run it for a few steps and find some nice point, because it's a reliable convergence. Reliable means that as long as you chose the ellipsoid in a proper way, you're squeezing it like this and finding a minimum, then you're getting actually pretty close to the minimum. It's not fast, especially, you know, the smaller the ellipsoid gets, the smaller the incremental change. If you look at this, the gradient, remember that in here, the A parameter, which is the step length gets smaller and smaller, and then this B, this scaling factor here, becomes closer and closer to 1, and also the C scaling factor is proportional to our step length. So this it's actually not getting smaller very fast, especially as the number of iterations grows bigger. But given that if we have a good strategy for choosing the original ellipsoid and we run it for some number of steps that we're satisfied with, we can narrow down the region where we find the minimum. And then when we've narrowed that region down, we have a good starting point for, let's say, Newton method or quasi-Newton method or something like this. So this works pretty well then. All right. These are the methods that we have. And these are all the methods basically that we're going to be asking about during the exam as well. And one more thing will be presented. That would be the extended cutting plane method, which I will explain on Thursday. But other than that, these lectures will no longer be producing anything new. So we've kind of covered the material now. So we will still be doing the exercises this week and next week, and you know, of course, and even had the lectures next week. I'm going to do a little bit of a revision of what we do, a quick revision next week, and then there will be time for questions and answers. And I'm going to stop the recording now, and we are